In the previous lecture, we looked at how we design instrumentation amplifiers and how to choose the resistor values and use these in an application. In this lecture, we're going to look at some more details of instrumentation amplifiers and look at some real applications that you may require to use an instrumentation amplifier in when you're doing your design projects. A classic application for an instrumentation amplifier is for audio applications. Here we have a typical example for an audio application. We've got a microphone which can produce a maximum output voltage of 100 millivolts and is connected to a mixing desk. However, the difference in the ground potential between the microphone ground, perhaps on the stage, and the mixing desk ground, which may be several hundred meters away, is 1 volt RMS, and it has a 50 Hertz frequency on it. If we just took the signal directly from the microphone and connected to the mixing desk, we would have the 50 Hertz interference signal sitting and adding on to the signal from 100 millivolts from the microphone, and the system, although it would produce noise, would be very, very distorted and full of interference. However, if we use an instrumentation amplifier to amplify the different signal coming from the microphone and rejecting the noise from the microphone ground, then we can actually receive the audio signal from the microphone and get high quality audio out of it. This application always assumes that the common mode gain of the instrumentation amplifier is much less than the differential gain, or AV. So let's do the analysis. So if the amplifier has a ratio between differential gain and common mode gain equal to CMRR of 10, then the microphone signal would have an amplitude equal to the signal appearing from the 50 Hertz signal. Well, that's not going to be very good because we're trying to listen to the person singing on stage. We want to get a much better CMRR. So let's make an assumption. If we want the microphone signal to be 1,000 times larger than the signal from the 50 Hertz, we now require a common mode rejection ratio of 10,000 or 80 decibels. To get such a high common mode rejection ratio, we would use a 3 op-amp instrumentation amplifier and put all the gain we can on the input stage. Let's assume we have plus or minus 15 volt power supplies, and let's also assume that the output from the amplifier can be no larger than 10 volts. So now we have a differential gain of 10 volts at the output of the instrumentation amplifier divided by the level of signal from the microphone of 100 millivolts, which gives us 100 times gain for the amplifier. If we want a common mode rejection ratio of 80 decibels or 10,000 times, let's put all the gain into the front stage. Our input gain would be a gain of 100 times, and the differential gain from the input stage would be 100, but the common mode gain, as we proved in the previous lecture, would only be 1 times. At the output, we would have a common mode gain of 100 divided by 100,000, which equals about 0.1. That would imply the use of 0.5% resistors around the difference stage of the instrumentation amplifier. So in this example, here's our final design. We've got two op-amps for the input stage of the instrumentation amplifier, and around that we have feedback resistors of 49.5 k ohms and 1 k ohm. 49.5 k ohm is RA and 1 k ohm is RB. Similarly, we have, I've chosen 10 Ks to be all the same resistors around the difference amplifier, and we've already specified them as 0.5% tolerance. And this is our final answer. The key thing to note in this example here is the microphone ground is not the same as the mixer ground. They are two different sources of signal, and in the example we've given, there was a 1 volt signal across those two grounds. But using this approach here, we would land up with a high quality audio output to the mixer and in the presence of a relatively large common mode signal of 1 volt RMS at 50 Hz. We've talked a lot about how we can improve the common mode rejection ratio, but what happens if we actually change the tolerances and matching around the input stage of an instrumentation amplifier? Here we've got the same circuit, and I've coloured RA as red for normal, but also I've considered RA as green for a mismatched between the RAs. What actually happens to our output stage? In the common mode gain situation, if the in plus is the same and equal to the in minus, which is the common mode definition, then what does our calculations look like here? We can now say our differential gain, which we know to be RA plus RA in green plus RB upon RB, remains similar, but our common mode gain remains the same, because at the top amplifier, the positive input is at in plus, which forces the negative input to also be at in plus. So we have the output at out plus. On the opposite amplifier, on the negative side, we have in minus connected to the non-inverting input, and the same voltage in minus is connected to the inverting input. Since there is no current flow through RA and no current flow through RB, then the gain must remain as a common mode gain of 1. Mismatches in RA give error in the differential gain accuracy of the overall instrumentation amplifier, but does not affect the common mode accuracy. And in this example, we're assuming that the common mode gain and differential gain for the difference stage, the second stage of the instrumentation amplifier, remains the same of R1 and R2. We've looked at instrumentation amplifiers, and we've proven that common mode rejection ratio is independent of RA match. We've also proven that common mode rejection ratio is proportional to the input stage gain of an instrumentation amplifier. And finally, the common mode rejection ratio is proportional to the R1, R2 match in the difference amplifier if we actually put gain in the difference amplifier. Does this mean that we can get any common mode rejection ratio from this type of amplifier whatsoever? In other words, if we had an input gain of 80 dB or 10,000 times, and we had R1 over R2 match of 0.01%, does that mean we can get a common mode rejection ratio equal to 154 dB? If we had a 1 volt common mode input signal, that would correspond to a 20 nanovolt differential signal at the inputs. That sounds like an incredible opportunity, and it'd be a very high performance circuit. Unfortunately, it doesn't work as well as that. The reason is that throughout our arguments and throughout our discussions looking at instrumentation amplifiers, we have always assumed perfect op-amps. Unfortunately, the world does not exist where we have perfect op-amps. And in the next lecture, we'll look at the impact of op-amp common mode rejection ratio and onto the final performance of the instrumentation amplifier common mode rejection ratio. Thank you.